So imagine you are looking at the Earth's crust. Like if you were to take a massive scoop of it, just a giant scoop of dirt, put it on a scale, and catalog every single element inside, you'd find that one specific metal is practically everywhere.
Right. It's incredibly common.
Yeah, it's the ninth most abundant element on the entire planet. I mean, it makes up nearly 1% of the crust by mass. It is literally sitting in the dirt in your backyard right now.
Which is wild when you think about it.
It is. But here is the paradox that we are going to unpack today. Despite it being absolutely everywhere, it took human beings a staggering 119 years after its initial discovery just to isolate a single pure sample of it.
Yeah, it is a remarkable contradiction. You have an element that is, incredibly common, yet so stubbornly inaccessible that it basically defied the greatest chemical minds of the 18th and 19th centuries.
Welcome to the deep dive. Today, we are completely deconstructing an element that you interact with every single day, probably without even realizing it.
Yeah.
We're talking about titanium.
A fascinating topic.
And to do this justice, we've pulled a massive, incredibly diverse stack of sources for you. We're looking at current 2025 industrial market reports, cutting-edge biomedical research on bone implants.
Some really amazing medical stuff in there.
Oh, absolutely. Plus geological studies analyzing the very oldest rocks on Earth and, some incredibly detailed metallurgical fact sheets.
And we really need that breadth of sources because, well, the story of titanium just does not fit neatly into one discipline.
No, it really doesn't.
Yeah.
So our mission today is to show you how this single wonder metal acts as this sort of connective thread. We're going to trace it from the violent formation of the Earth's very first continental crusts,
right,
through the highly stressed, complex realities of modern global supply chains, all the way to the future of human biology and surgical implants.
It's a vast journey for sure. But the underlying physics and chemistry of the element, they remain exactly the same throughout all of those contexts. And I think that's what makes it so fascinating.
Yeah, totally. So let's start with that initial paradox, because the history of how we even found this stuff kind of sets the stage for everything else. It was discovered back in 1791 by this British mineralogist and clergyman named William Gregor.
Yeah, clergyman, which is just classic 18th century science.
Right. So he found some weird black magnetic sand in a stream in Cornwall, treated it with hydrochloric acid, and realized there was this white residue left over that just didn't match any known element. But he couldn't isolate the metal itself.
Exactly. He just knew something novel was in the ore, but that was it.
So then 4 years later, in 1795, a German chemist named Martin Heinrich Klaproth independently discovered the exact same thing in a different ore. He couldn't isolate the pure metal either, but he was so impressed by the sheer, unyielding strength of the chemical bonds holding this mystery substance together.
Right. He knew he was dealing with something intense.
Yeah, so he decided to name it after the Titans of Greek mythology.
Which is incredibly poetic, right? And scientifically accurate. I mean, the Titans were known for their immense primordial strength. Klaproth recognized that tearing this element away from the oxygen it was bonded to was going to require a Herculean or, well, perhaps Titanic effort.
Okay, let's unpack this. Because it took until 1910, 119 years later, for a metallurgist named Matthew A. Hunter to finally isolate 99.9% pure titanium. Why did it take so long? I mean, if it's the ninth most abundant element, why couldn't they just smelt it out of the rock like iron or copper?
Well, it really comes down to the element's thermodynamic personality, if you want to call it that. On a chemical level, titanium is incredibly social. Yeah, it absolutely refuses to exist in isolation in nature. It is always, always stubbornly bonded to other elements, most commonly oxygen, forming titanium dioxide. And the bond energy between titanium and oxygen is extraordinarily high. It is a highly stable, low-energy state that the universe essentially favors.
So nature just naturally wants it to be a compound.
Precisely. If you want to separate them, you can't just apply sheet like you would with, say, iron ore in a traditional blast furnace.
Right.
If you just heat up titanium dioxide with carbon, you don't get pure titanium metal. You actually get titanium carbide, which is this brittle ceramic material. So early chemists were using the tools of the 18th and 19th centuries to fight a thermodynamic battle they literally couldn't win. They were trying to pry apart two atoms that are essentially welded together at the quantum level.
And once we finally did figure out how to break those bonds, we realized just how strange this element really is.
Yeah.
Like, Reading through the metallurgical fact sheets we gathered for you, the list of physical properties feels almost contradictory.
Oh, absolutely. It's full of extremes.
Right. For instance, it is found in trace amounts in almost every living thing. It's incredibly corrosion resistant.
Mm.
The sheets point out that you can drop a piece of pure titanium into seawater or expose it to industrial chlorine gas, and it just laughs it off. It doesn't rust.
And the mechanism behind that corrosion resistance is brilliant. It's not that titanium doesn't react with its environment. It's actually that it reacts instantly and perfectly.
But what do you mean by perfectly?
Well, the millisecond pure titanium is exposed to air or moisture. It forms a microscopic, continuous, impenetrable layer of titanium dioxide on its surface. It's called a passive oxide layer.
So it basically instantly builds its own armor out of the very oxygen that's trying to attack it.
Exactly. It uses the enemy against itself. And if you scratch that armor off, it regrows in a fraction of a second. That impenetrable shield is what stops the seawater or the harsh chemicals from reaching the bulk metal underneath.
But then in the very next paragraph of the metallurgical sheet, it notes that if you put titanium in a pure nitrogen atmosphere, it'll actually burn, like it catches fire.
Yeah, it's one of the only elements that will actively burn in nitrogen gas.
Which is wild.
Yeah.
I mean, we think of nitrogen as an inert gas that we use to put fires out. And beyond the extreme chemistry, it has this incredible aesthetic quality. The architectural world loves it. The entire Guggenheim Museum in Bilbao, Spain, is covered in tens of thousands of paper-thin titanium panels.
And the reason architects love it is actually because of that same passive oxide layer we just talked about.
Really? The armor?
Yeah. By using an electrochemical process called anodizing, you can precisely control the thickness of that oxide layer at the nanometer scale. And depending on the exact thickness, the layer refracts incoming light differently, which creates these brilliant iridescent colors without using a single drop of dye or pigment.
So for you listening right now, whether you were applying sunscreen before going to the beach, staring at a bright white painted wall in your living room, or admiring the silver frame of a high-end racing bicycle, you are looking at titanium.
You really are. It's everywhere.
But the titanium in your sunscreen is fundamentally different from the titanium in a jet engine.
They are two entirely different manifestations of the same element. And to really understand why it dictates our global economy today, we have to clearly separate its two distinct alter egos.
Yeah, let's start with what we'll call the metallic muscle. When we think of titanium metal, we usually picture a solid machine block holding an airplane wing together. But in modern advanced manufacturing, it very often starts as a fine silver gray metallic powder, right?
That's right.
And the primary claim to fame for the metal form is its strength-to-weight ratio. It boasts the structural strength of steel, but it comes in at almost exactly half the weight.
That ratio is the absolute holy grail for engineers. I mean,
Yep.
if you are building a spacecraft, a fighter jet, or even a high-performance car, weight is your ultimate enemy.
Because it's expensive to move heavy things.
Exactly. Every extra ounce you carry costs you fuel and compromises your efficiency. With titanium, you get the structural integrity required to survive immense G-forces and physical stress without the massive weight penalty you'd get from using steel.
And the sources also emphasize its high thermal stability.
Yes, meaning it retains that strength even when things get incredibly hot. Like aluminum is very light, but it softens and loses its structural integrity at relatively low temperatures.
Which is bad for a jet engine.
Very bad. Titanium holds its shape and strength in environments that would literally turn aluminum to a liquid, which is exactly why it's used in the high-pressure compressor blades of jet engines.
And crucially, for the 2025 industrial landscape we're looking at, this powdered form of the metal is perfect for 3D printing or additive manufacturing.
Additive manufacturing has completely revolutionized how we use titanium. What's fascinating here is that instead of taking a massive, expensive block of the metal and milling it down where you're wasting up to 90% of the material as scrap shavings, you use high-purity titanium powder.
Oh, so there's way less waste.
Exactly. A laser essentially melts, or sinters, the powder layer by microscopic layer. This allows engineers to design these incredibly complex internal honeycomb structures that are mathematically impossible to machine with traditional tools. So you're creating parts that are even lighter and stronger.
But the sources flagged a major hazard with this powder that totally caught me off guard. We just talked about how titanium is used in jet engines operating at terrifying temperatures. But in its powdered form, it is highly flammable.
It is a severe industrial hazard. And I know it seems counterintuitive, but it really comes down to surface area to volume ratio and oxidation kinetics.
Okay, walk us through that mechanism. Why does a solid block survive a jet engine, but a pile of the exact same powder catches fire?
Well, remember that passive oxide layer?
The instant armor.
Right. In a solid block, that layer forms on the outside and protects the massive volume of metal underneath. But when you pulverize titanium into a fine dust, you are drastically increasing the exposed surface area relative to the volume. Every microscopic particle is pure, highly reactive metal just waiting to oxidize.
Oh, man. So it's like thousands of little bombs.
Basically, if you introduce a spark or even significant friction to a cloud of titanium dust in the air, the oxidation reaction happens simultaneously across billions of particles.
Because oxidation is an exothermic reaction, right? It releases heat.
Exactly. The rapid oxidation releases an immense amount of thermal energy all at once, which we perceive as an intense, brilliant white fire or even a full-blown explosion. So handling this powder for 3D printing requires specialized inert gas environments and incredibly strict safety protocols.
Okay, so that is the metallic alter ego, the muscle. But the other face of titanium is actually far more common in our daily lives, and it doesn't look like a metal at all. We are talking about titanium dioxide, or TiO2. This is the ubiquitous white pigment.
And physically, chemically, it behaves completely differently. The sources describe TiO2 as an amphoteric oxide.
Okay, let's break that term down because it's important. What does amphoteric actually mean in practice?
Amphoteric just means that it can react as both an acid and a base, depending on the chemical environment it finds itself in, so it is chemically very versatile.
Yeah.
But for commercial purposes, its most valuable properties are optical, not structural. It is a non-toxic, brilliant white powder.
The metallurgical sheets emphasize its unparalleled opacity and its exceptionally high refractive index.
Right. The refractive index measures how much a material bends and scatters light. Diamond, for example, has a very high refractive index, which is why it sparkles.
Right.
Titanium dioxide actually has a higher refractive index than diamond.
Wait, really? Higher than diamond?
Higher than diamond. When light hits a particle of TiO2, it bounces and scatters incredibly efficiently. That's why it is the global gold standard for making things white. When you put it in paint, plastics, or paper, it scatters practically all visible wavelengths of light right back at your eye, creating this staggering, opaque whiteness.
And as I mentioned earlier, it's exactly how it works in sunscreen. It's not absorbing the UV radiation chemically. It's acting as millions of microscopic physical mirrors, literally bouncing the harmful UV rays away from your skin.
But the research sources point out that TiO2 is not always just a passive mirror. It actually has a hidden talent called photocatalytic activity.
Yeah, this is where it gets really sci-fi.
It really does. When you expose specific crystal structures of titanium dioxide to ultraviolet light, it kind of wakes up. The UV light carries enough energy to knock electrons out of their normal orbits in the TiO2 crystal. This creates what we call an electron-hole pair.
Okay.
These loose electrons and the holes they leave behind migrate to the surface of the particle and interact with moisture in the air.
And what does that interaction do, like practically speaking?
It generates highly reactive molecules called hydroxyl radicals. These radicals act like microscopic chemical buzzsaws. They will violently tear apart the molecular bonds of any organic pollutants, bacteria, or volatile organic compounds they touch.
Wow.
Ultimately breaking them down into completely harmless carbon dioxide and water.
So we aren't just using TiO2 to make our walls look perfectly white. We're using this photocatalytic property in advanced environmental engineering. Like you can coat the side of a building, or an air purification filter, or a wastewater treatment plant with TiO2, shine UV light on it, and it actively eats smog and bacteria.
Yeah, it literally creates a self-cleaning surface.
It is a profound application of the material. But this brings us to a massive logistical problem that drives the modern market.
Right. The supply chain issue.
Yeah, and this is where I want to push back on the industrial logic here, because the math feels wrong. If this brilliant white powder, TiO2, is just sitting there in the dirt, if it's the 9th most abundant element, and we mine it by the millions of tons to make house paint and self-cleaning concrete, why is getting the pure silver metallic titanium for 3D printing in aerospace so incredibly hard and astronomically expensive? I mean, they are the exact same base element.
I like to use an analogy for this. Imagine you have a beautifully baked cake. The flour, eggs, and sugar are perfectly bonded together through the heat of the oven. Now, I ask you to unbake that cake.
Unbake it?
Yeah. I want you to separate the flour back into a pristine white powder and put the raw eggs back in their shells.
That sounds physically impossible without destroying everything.
It nearly is. And unbaking the titanium dioxide cake to get pure titanium metal requires an industrial method known as the Kroll process. And I have to tell you, the Kroll process is an alchemical nightmare. It is an exercise in sheer thermodynamic brute force.
Okay, so how do we do it?
Yeah.
What is the actual physical process of unbaking this cake? Because if it took us over a century to figure out, it can't just be a simple furnace.
No, it is a massive, highly volatile, multi-stage operation. The process was invented by Wilhelm Kroll, a metallurgist who fled Europe in the late 1930s and brought his research to the United States. He figured out that to break that ultra-strong titanium-oxygen bond, you had to use chemical leverage, not just heat.
Okay, so step one is chlorination.
Yes. You start with your raw TiO2 dirt, you mix it with carbon, usually in the form of petroleum coke, and you hit it with chlorine gas at extreme temperatures, around 1,000 degrees Celsius.
So you're basically using a 1,000-degree blowtorch and a chemical crowbar.
Exactly. At that temperature, the carbon is able to steal the oxygen atoms away to form carbon dioxide gas, while the highly reactive chlorine gas simultaneously rushes in to bond with the freshly exposed titanium. What you are left with is a substance called titanium tetrachloride, or TiCl4.
But TiCl4 isn't a metal.
No, not at all. It's a highly volatile, corrosive liquid at room temperature. It fumes heavily in moist air. So we've basically turned solid dirt into a nasty, fuming liquid.
Right.
Now we move to step 2, purification. Because the initial dirt had a lot of impurities, iron, vanadium, silicon, those all got chlorinated too. So you have to put this liquid through fractional distillation, boiling it at precise temperatures to separate the pure TiCl4 from the other metal chlorides.
Okay, just like refining crude oil into gasoline.
Exactly like that. Now you have purified TCl4, but you still don't have titanium metal. You just have titanium trapped with chlorine instead of oxygen. So step 3 is reduction, and this is the truly brutal, energy-intensive part.
Because now we have to pry the chlorine off.
Yes. You pump your purified liquid TiCl4 into a massive, sealed stainless steel reactor vessel. Inside that vessel is molten magnesium metal, heated to around 800 or 900 degrees Celsius. And you have to do all of this in an absolute vacuum or in an inert argon gas atmosphere.
Because remember, pure titanium will instantly react with oxygen or nitrogen.
Exactly. So the magnesium acts as a reducing agent. It fundamentally strips the chlorine atoms away from the titanium. Thermodynamically, the chlorine actually prefers to bond with the magnesium.
Oh, interesting.
So it detaches from the titanium, forms liquid magnesium chloride, and leaves behind pure metallic titanium. But, and here's the catch, it doesn't form a nice solid block. It forms this porous, weird-looking mass that metallurgists literally call titanium sponge.
Wait, sponge. So we have a sponge of pure metal, but it's just soaking in liquid magnesium chloride and leftover molten magnesium.
Yes, which leads to the final step, separation. You have to let this massive reactor cool down, which can take days. Then you literally chisel or machine this giant sponge out of the reactor. Finally, you have to put that sponge into a vacuum distillation furnace and bake it at high temperatures to boil off the remaining microscopic traces of magnesium and magnesium chloride.
And then finally you have pure titanium.
Right, leaving you with pure elemental titanium sponge, which can then be melted down into ingots or turned into powder.
Honestly, hearing the sheer scale of that, the extreme heat, the handling of highly toxic chlorine gas, the use of expensive molten magnesium, the days of cooling, the vacuum chambers, it completely answers the paradox. Like the abundance of the element in the ground simply does not equal an abundance of the metal in the market. The bottleneck isn't the earth. The bottleneck is the physics of the Kroll process.
Precisely. And that physical bottleneck, that painful transition from dirt to metal, sets the stage perfectly for what is happening right now in the global economy. Because when we look at the 2025 industrial market reports from our sources, this supply chain is under severe, unprecedented stress.
Yeah, the demand is skyrocketing, but the physics of producing the metal remain incredibly stubborn. Let's talk about the U.S. manufacturing renaissance. According to the 2025 reports, the domestic market is absolutely buzzing. We are seeing massive reshoring trends. Companies are actively bringing their manufacturing base back to the United States.
Driven heavily by federal policy, of course.
Right. You have the CHPS and Science Act, which is pouring billions into domestic semiconductor manufacturing. Semiconductors require ultra-high purity titanium for internal components and deposition processes. Then you have the Inflation Reduction Act, which is driving billions of dollars into aerospace and electric vehicle production.
EVs are a major driver right now. While a traditional combustion engine might use some titanium, electric vehicles demand advanced lightweighting to maximize battery range.
Every ounce counts.
Every single ounce, every pound you save on the chassis or structural components translates directly to extra miles of range. And aerospace, of course, has always been the primary consumer of the highest grade titanium alloys.
So the demand is hitting from all sides. The reports show U.S. demand for titanium dioxide, just the white powder for coatings, advanced materials, and battery tech, is projected at a massive 1.2 million tons for 2025 alone.
That is a staggering amount.
It is. And the pricing completely reflects the insanity of that Kroll process we just discussed. The sources note that industrial TiO2, the cake before it's unbaked, costs anywhere from $2,800 to $3,500 per ton. But the pure titanium metal, it's running $20 to $30 per kilogram.
It's a completely different stratosphere of pricing. It really highlights the massive value add and the massive energy add of unbaking the cake. And ensuring that this material actually reaches the assembly lines requires a highly orchestrated global supply chain.
Yeah, the sources list some of the key corporate players who are currently trying to navigate this minefield. On the TiO2 side, you have Chemours, a massive U.S. chemical company. They are producing around 400,000 tons of TiO2 annually. But what the sources highlight is that Chemours leads with something called a chloride process, which supposedly cuts their waste generation by 30% compared to older methods.
This is a critical technological shift. Historically, the industry used the sulfate process to extract TiO2 from the raw ore.
Okay, how does that differ from what Chemours is doing?
Well, the sulfate process uses concentrated sulfuric acid to dissolve the ore. It is notoriously dirty. It generates vast amounts of acidic, iron-rich liquid waste that has to be neutralized and disposed of, which is a massive environmental headache. The chloride process, which is conceptually similar to the first step of the core process, using chlorine gas at high heat, is much cleaner.
Wait, why is it cleaner? Chlorine gas sounds just as dangerous, if not more so.
It is incredibly dangerous to handle, yes, but the process is continuous and highly efficient. The chlorine gas reacts with the ore to form titanium tetrachloride. The impurities are separated out as solid chlorides rather than oceans of liquid acid. And then the TiCl4 is oxidized back into pure TiO2.
Right.
The brilliant part is that the chlorine gas is released during that final oxidation step and is captured and recycled right back into the front end of the plant. It's a closed-loop system, which drastically reduces the volume of waste.
So Chemours leaning into the chloride process is a necessary adaptation to meet modern environmental, social, and governance, or ESG goals, as outlined in the market reports.
Exactly. The industry has to adapt. You also have companies like Tronox who operate on a model of massive vertical integration. They literally own their own ilmenite mines in places like South Africa and Australia.
Ilmenite being the raw rock, the ore that contains the titanium.
Right. By owning the mines, the shipping, and the chemical refining plants, Tronox insulates itself from the volatility of raw material prices. They control the dirt all the way up to the finished white powder.
And on the pure metal side, for the aerospace demand, you have companies like ATI Allegheny Technologies and Timet. They focus intensely on taking that titanium sponge from the Kroll process, melting it down in massive vacuum arc remelting furnaces, and alloying it for specific aerospace needs.
But, we cannot discuss these U.S. manufacturing titans without addressing the elephant in the room, global geopolitics.
Right. Because despite this U.S. renaissance, the sources are crystal clear on who actually controls the raw material. China currently produces the most titanium in the world, followed closely by Russia.
Which immediately injects massive systemic vulnerability into the entire U.S. supply chain.
Exactly. You have companies like China's Lohmann Billions, which is a juggernaut in production. But because of ongoing trade disputes detailed in the reports, their products face 10 to 25% U.S. tariffs.
Right.
I mean, if you were a U.S. manufacturer buying raw materials, a 25% tax immediately destroys your profit margin. And then you have Russia's VSMPO Avisma. The sources note they are actually the world's largest single producer of titanium metal. They historically supplied Boeing and Airbus with massive titanium forgings for landing gear and wing structures.
But due to the geopolitical climate and heavy sanctions, Western access to that Russian metal is severely restricted.
So if you're a U.S. aerospace company, you are caught in a vice. You are desperate for this metal to build next-generation tech, but the two largest suppliers on the planet are locked behind tariff walls or geopolitical sanctions. Which makes me ask the obvious question. If the demand is so high and we have all these federal subsidies flowing, Why aren't we just building more titanium factories in the U.S. overnight? Like just spin up a dozen new Kroll process plants in Nevada or Texas.
It's the logical next step, sure, but it's not just about capital. It's about severe physical and human bottlenecks. First, the U.S. is facing a historic labor shortage in the manufacturing sector. The market reports in our sources project up to 800,000 unfilled manufacturing jobs in 2025.
And as we discussed with the Kroll process, you aren't just hiring someone to turn a wrench.
Exactly. You cannot run a highly complex, phenomenally dangerous chemical refinery dealing with 1,000-degree reactors and chlorine gas without highly trained, specialized operators. The labor pool simply isn't there to scale up rapidly. Second, and perhaps more importantly, is the cost of energy.
Because unbaking the cake takes immense electricity.
Vast amounts. The energy costs in the U.S. are running 20 to 30% higher than in China. Our industrial rates are hovering around 12 to 15 cents per kilowatt hour in many manufacturing hubs. When you are boiling liquid metal in a vacuum, your energy bill is your primary operating expense.
Wow, yeah.
That energy delta alone acts as a massive deterrent to building new greenfield domestic Kroll capacity.
And finally, even if you secure the funding, train the workers, and pay for the power, you still have to get the raw ilmenite ore from friendly nations. And global supply chain disruptions, like the ongoing maritime shipping delays through the Red Sea and the Suez Canal, are adding incredible friction, lead times, and insurance costs to every single shipment of raw dirt.
So how does the industry survive this? They can't just sit still and wait for the geopolitics to resolve.
They aren't. The reports show rapid, forced innovation. To offset the labor shortages, these metallurgical plants are heavily investing in AI and robotics. They are automating the dangerous refining steps and using machine vision for quality control to maximize output with a smaller workforce.
And to fight the crippling energy costs and emissions, you see companies like Kronos aggressively investing in solar-powered refining facilities. They're essentially trying to uncouple their energy needs from the volatile fossil fuel grid.
And perhaps the most impactful adaptation. The industry is getting incredibly good at recycling.
This is the circular economy in action.
Yeah, the sources state they are now recycling up to 30% of titanium scrap. So instead of starting from raw TiO2 dirt and suffering through the entire Kroll process every single time, they were taking the titanium shavings, the scrap left over from milling those airplane parts, purifying it, and feeding it right back into the melting furnaces.
It bypasses the chemical bottleneck entirely.
Exactly. So, to you, the listener, the next time you buy a premium white cosmetic product, or you sit in an airplane seat and look out the window at the massive engine housing, realize that you are directly interacting with this incredibly tense, highly orchestrated global machine. It is a delicate, high-stakes dance of geopolitics, energy grids, tariffs, and advanced chemistry.
It's a marvel of human logistics. But as complex as it is to navigate a global supply chain to put titanium into a jet engine, that complexity absolutely pales in comparison to what happens when we try to put titanium into a living human being.
And this is where we completely shift gears. We are moving from macroeconomics and industrial furnaces into the microscopic world of biology, the medical marvel of titanium. Here's where it gets really interesting.
This is the point in our deep dive where titanium stops being just an inert structural material and becomes an active, almost miraculous biological partner.
Let's talk about how biology reacts to this metal. In our biomedical sources, there is a foundational concept called osseointegration.
A huge term in the field?
Yeah, the term was coined by a Swedish researcher named P.I. Brainmark back in the mid-20th century, though it really became the global standard in the 1980s. Brainmark was actually studying blood flow in rabbit bone. He surgically implanted a tiny titanium optical chamber into a rabbit's leg to view the blood vessels. And when the experiment was over, he tried to remove the titanium chamber.
And he couldn't.
He literally couldn't get it out. I mean, the human body and mammalian biology in general is notoriously hostile to foreign objects. If you get a splinter of wood, a shard of glass, or even a piece of stainless steel stuck in your arm, your immune system immediately identifies it as an invader.
It attacks it.
Right. It triggers an inflammatory response, walls the object off with thick, fibrous scar tissue, and slowly tries to push it out of the body.
But titanium behaves completely differently. The body doesn't reject it. It doesn't even just tolerate it. The bone actively embraces it.
Osseointegration is defined as the direct, structural, and functional connection between living bone and the surface of an artificial implant. The bone treats the metal like it's part of the skeleton. Why does this happen? I mean, we just spent half an hour talking about how unnatural this metal is.
It all goes back to that very first physical property we discussed, the passive oxide layer.
The armor again.
Exactly. When a surgeon places a titanium implant into your jaw or your femur, the body doesn't actually touch titanium metal, it touches titanium dioxide. To the body's immune system, that specific ceramic oxide layer does not register as a biological threat. It essentially mimics the inorganic mineral components of natural bone.
So it's a form of biochemical camouflage.
Exactly. The moment the implant is placed, blood proteins instantly adhere to that oxide surface. Then, specialized cells called osteoblasts, which are the microscopic builders responsible for laying down new bone tissue, migrate directly onto the titanium.
Just latch onto it.
Yeah, they attach to the microscopic pores and roughness of the metal, and they begin secreting calcium and phosphate. The living bone actually grows into the topography of the metal. It becomes one unified structural matrix.
It is essentially cyborg science. Yeah. And this discovery has been the absolute foundation of joint replacements, spinal fusions, and dental implants for decades. Millions of people walk around every day because of osseointegration.
Yeah.
But, and this is a massive but, raised by our biomedical sources, there is a major problem with the current commercial standard.
Yes, the industry standard titanium alloy used for the vast majority of implants right now is an alloy called Ti6Al4V.
Okay, let's decode that formula.
It stands for titanium blended with 6% aluminum and 4% vanadium. By blending those elements, metallurgists created an incredibly strong, fatigue-resistant metal.
But our research points out that while it's great for an airplane, it has serious flaws when you place it inside the warm, wet, dynamic environment of the human body for 10, 20, or 30 years.
The issues are really twofold. One is chemical toxicity, and the other is mechanical incompatibility. Let's look at the chemistry first. Vanadium is a heavy metal, and it is highly toxic to human biology. Over decades, as an implant undergoes microscopic wear and tear from daily movement, trace amounts of vanadium ions can slowly leach out of the alloy and into the surrounding tissue.
And the body has no mechanism to deal with that.
No. Long-term accumulation of vanadium has been flagged in numerous studies as highly cytotoxic, meaning it actively kills cells, and it is considered a potential cancer risk.
What about the aluminum? Is that any better?
Aluminum isn't much better, no. Its slow accumulation in the body, particularly in the bone marrow, has been linked to osteomalacia, which is a dangerous softening and weakening of the bones. It has also been implicated in various long-term neurological disorders. So, continuously dosing a patient with trace amounts of toxic heavy metals over their lifespan is obviously a medical flaw we need to fix.
But the mechanical problem they highlighted is arguably even more fascinating because it deals with the fundamental physics of how we move. It has to do with stiffness. In material science, stiffness is measured by something called the elastic modulus. The elastic modulus of this standard Ti6Al4V alloy is around 110 gigapascals, or GPa.
Gigapascals being a unit of pressure measuring how much force it takes to deform the material.
Right. 110 GPa is incredibly stiff. But human cortical bone, the hard outer layer of your femur, for instance, is much more flexible. Its elastic modulus is only around 30 GPa.
Which means the metal implant is roughly 3 to 4 times stiffer than the bone it is attached to. And this mismatch creates a severe biomechanical phenomenon known as stress shielding.
Okay, to understand stress shielding, think of it like doing a group project in school, where the titanium implant is that one intense overachiever who insists on doing all the heavy lifting. When you walk or jump or lift something heavy, force is transmitted through your skeleton. If you have a solid, super stiff titanium rod in your leg, the force takes the path of least resistance. The titanium implant takes on almost all the physical stress because it simply won't bend.
And because the implant does all the physical work, the actual living bone tissue surrounding the implant gets lazy. It doesn't feel the mechanical stress anymore. It is literally shielded from the load.
And in human biology, the golden rule is, if you don't use it, you lose it.
Exactly. Bone is not a dead stick. It is a highly dynamic, constantly remodeling organ. This remodeling is governed by a physiological principle known as Wolff's Law.
Wolff's Law?
Yes, Wolff's Law dictates that bone tissue will adapt to the mechanical loads it is placed under. The underlying mechanism involves the piezoelectric effect.
Which is what exactly?
When bone is compressed, the crystalline matrix of the bone actually generates a tiny electrical charge. This electrical signal tells the osteoblast cells, we are under stress, build more bone here to handle the load.
Ah. But if the titanium is taking all the stress, there is no compression, no electrical signal, and no instruction to build.
Precisely. The body assumes that the bone surrounding the implant is no longer necessary. So cellular demolition crews called osteoclasts move in and begin tearing the bone down, reabsorbing the calcium back into the bloodstream. Yeah, the bone literally thins out and wastes away over time. Eventually, the bone recedes so much that the massive titanium implant becomes loose, leading to severe pain, structural failure, and the need for a highly invasive revision surgery to replace it.
So the goal is clear. We need an implant that is strong enough to not break when you jump, but flexible enough to let the living bone do its fair share of the group project. We need the implant to bend just a little bit so the bone feels the stress and stays healthy. And our sources detail a massive cutting-edge breakthrough in this exact area, a novel beta titanium alloy.
This is where advanced metallurgical engineering intersects perfectly with biology to solve the stress shielding crisis once and for all.
The researchers engineered an ultra-fine-grained beta titanium alloy. The specific chemical formula they landed on is a bit of a mouthful. Ti-35NB7ZR5TA98 Psi2.
Let's break down why that specific recipe is so brilliant. First, they looked at the chemistry. They completely removed the toxic aluminum and vanadium. Instead, they blended the titanium base with niobium, zirconium, and tantalum. These are all transition metals that are highly intrinsically biocompatible. They do not trigger cytotoxic reactions.
So the toxicity problem is solved. But what about the stiffness problem? That's where the end of the formula comes in. They added a tiny amount of silicon, just 2%. What exactly does the silicon do?
The silicon acts as what metallurgists call a grain refiner. They manufactured this new alloy using a highly advanced technique called spark plasma sintering, or SPS. Instead of just melting the metals together in a pot, they mix them as powders, put them under immense physical pressure, and blast them with high-voltage electrical pulses.
What does that achieve?
Well, when metals cool and solidify, they form microscopic crystalline structures called grains. Normally, those grains grow relatively large, but during the rapid cooling of the SPS process, the tiny amount of silicon atoms naturally migrate to the outer boundaries of these newly forming grains.
It's like little borders.
Yeah, the silicon literally acts like microscopic roadblocks, pinning the boundaries and preventing the titanium grains from growing any larger.
The result is an ultrafine grain structure. But why does grain size matter?
It comes down to a principle called the Hall-Petch relationship. The smaller the grains, the more grain boundaries you have packed into a given volume. These boundaries act as physical barriers that stop microscopic cracks and dislocations from spreading through the metal. Therefore, incredibly small grains equal incredibly high strength.
And the physiological stats on this new alloy are just mind-blowing. Remember, the old standard Ti6L4V had an elastic modulus of 110 GPa. This new silicon-refined beta titanium drops that stiffness all the way down to just 37 GPa. It almost perfectly matches the 30 GPa flexibility of living human bone.
But, and this is the absolute genius of the ultrafine grain structure, it doesn't sacrifice structural integrity to get that flexibility. It bends like bone, but it maintains a massive breaking strength of 263 megapascals. It is phenomenally strong, yet perfectly elastic.
So it looks perfect on paper. But does it actually work in a living, moving body? The biomedical sources walk us through a fascinating 3-month in vivo study to prove the concept. They manufactured tiny implant rods out of this new beta alloy and rods out of the old standard alloy. They surgically implanted them into the femurs of live rabbits.
Right.
They stitched them up and let the rabbits hop around normally for 3 months, allowing the bodies to heal and the bone to integrate with the metal.
The rabbit femur is an excellent model for human bone mechanics, and the data they extracted after 3 months clearly demonstrates the profound physiological impact of fixing that elastic modulus mismatch.
Right. After the 3 months, they sacrificed the rabbits and performed a mechanical push-out test on the femurs. They put the bone in a specialized machine and literally measured how much raw brute force in newtons it took to dislodge the implant and push it out of the bone tunnel.
The old standard stiff titanium required 284 newtons of force to push out.
But the new flexible beta titanium alloy, it required a massive 377 newtons of force to dislodge.
Yeah.
It was gripping the bone, or rather, the living bone was gripping the metal substantially harder.
And they didn't just measure the physical force, they verified exactly why this was happening microscopically. They sliced the bone incredibly thin and measured the bone implant contact ratio, or BIC.
What did that measure?
This measures exactly what percentage of the metal surface is in direct physical contact with healthy, mineralized bone tissue rather than soft scar tissue. The BIC C for the old stiff alloy was 73.31%. For the new flexible alloy, it jumped to 77.45%.
So synthesize this for us. Why did the bone grab onto the new alloy so much tighter? What was the cellular mechanism?
It is the ultimate validation of Wolff's law. Because the new alloy flexes exactly like the bone around it, it distributes the mechanical stress of the rabbits hopping evenly across the entire surface of the implant-bone interface.
It shares the load.
Exactly. The bone is no longer shielded from the work. Every time the rabbit lands, the metal bends slightly, compressing the bone. That compression generates the piezoelectric signal. The osteoblasts feel the stress. They recognize that they need to be strong to carry that load. And they respond by laying down dense, healthy, highly mineralized bone tissue that tightly anchors into the microscopic pores of the metal.
While with the older, stiffer alloy, the uneven stress distribution created dead zones. The lack of signaling allowed the body to form weak, fibrous scar tissue in certain areas instead of healthy bone, resulting in a much weaker grip.
Precisely. It's a huge difference.
It's incredible. By simply tuning the physical flexibility of the metal using a pinch of silicon, we are literally manipulating cellular behavior. We aren't using drugs. We're using mechanical physics to trip the body into building stronger bone.
It represents a massive paradigm shift in orthopedic medicine. We are moving away from just inserting inert, dumb structural props into the body. We are now designing biomaterials that actively participate in the body's biomechanical signaling network. The implant and the skeleton are literally communicating through physics.
Okay, so we've seen how titanium seamlessly integrates into living bone on a microscopic cellular level. Now, we are going to radically shift our perspective. We are going to zoom out, way, way out, from the microscopic growth of new bone tissue over 3 months to the macroscopic violent growth of the Earth's very first continents over billions of years.
A bit of a scale jump.
Yeah, just a bit, because the exact same element that integrates into our femurs is currently being used by geologists as a literal time machine to read the hidden history of our planet.
It is a beautiful scientific symmetry. The stubbornness of titanium, the immense chemical stability that made it take 119 years to isolate, makes it an incredibly durable recorder of geological events. Once a titanium atom locks into a specific crystal structure in a cooling pool of magma, it is trapped. It takes a planetary scale event to melt it and reset it.
To understand how we read this planetary memory, the geological sources introduce us to a specific, highly unusual mineral called Loveringite. It was discovered relatively recently, in 1978, in the Jimberlon intrusion in Western Australia. It was named after an Australian geochemist, John Francis Lovering.
Loveringite is visually unassuming but chemically fascinating. It's a rare, black, metallic oxide mineral. The chemical formula is incredibly complex. It's essentially a garbage can mineral that sweeps up elements as magma cools.
A garbage can mineral.
Yeah, it contains calcium, cerium, titanium, iron, chromium, magnesium, and oxygen, just a mix of everything. But for geologists, it acts as a highly resilient, titanium-rich time capsule.
The sources describe its physical properties when you look at it in a thin section under a polarized light microscope. It's opaque, it is highly resistant to chemical weathering, and it sticks out with high relief and sharp boundaries against the surrounding rock. But there's this one detail in the literature that sounds straight out of a sci-fi novel. Loveringite crystals are very often found in a metapanic state.
Yes, metamictization. This is a real testament to deep geologic time. When the Loveringite crystal first formed billions of years ago, its atoms were arranged in a neat, highly ordered geometric lattice. But occasionally, a trace atom of radioactive uranium or thorium gets accidentally trapped inside that crystal lattice during formation.
And uranium's unstable.
Right. Over hundreds of millions or even billions of years, that trapped uranium slowly decays, firing off alpha particles. This internal radiation acts like microscopic cannonballs, physically smashing into the surrounding atoms. Over eons, the radiation completely destroys the neat, orderly crystal lattice from the inside out, turning the internal structure of the mineral into a disorganized, glassy, amorphous blob. The mineral has literally been cooked by its own internal radiation.
Which just vividly highlights how unfathomably old the rocks we are talking about really are. But how does a mineral like this, or titanium in general, actually help us look back nearly 4 billion years? I mean, the crystal structure is destroyed, so what are we looking at?
Well, we aren't looking at the structure anymore. We are looking at the weight of the atoms themselves. We are relying on the cutting-edge science of measuring titanium isotopes.
How does weighing the atoms tell us anything about the early Earth?
Because different macroscopic geological processes sort the heavy and light atoms differently. Imagine a massive subterranean ocean of molten rock magma. As that magma slowly begins to cool, it doesn't all turn into solid rock at once. Different minerals have different melting points, so they crystallize and precipitate out of the liquid at different times. This process is called fractional crystallization.
Okay, like freezing a mixture of water and alcohol, right? The water freezes into ice first, leaving a stronger alcohol liquid behind.
Exactly like that. Now, when titanium-bearing minerals like ilmenite or rutile begin to crystallize in that cooling magma, they have a choice. They can grab a light titanium-47 atom or a heavy titanium-49 atom. Because of the microscopic kinetic energy differences in the chemical bonds, the solidifying crystals preferentially gobble up the light titanium isotopes. It is slightly easier for the light atoms to lock into the solid lattice.
So solid crystals packed with light isotopes sink to the bottom of the magma chamber.
Yes, which means the remaining liquid magma, which hasn't solidified yet, is now slightly depleted in light isotopes and therefore relatively enriched in the heavy titanium isotopes. As that liquid magma continues to rise, evolve, and eventually erupt or cool to form the continental crust, that new crust inherits that heavy isotope signature.
Ah, I see.
By measuring the ratio of heavy to light isotopes expressed as delta 4947, geologists possess a chemical fingerprint of the exact thermodynamic journey that magma took before it became rock.
And this raises one of the most profound questions in all of Earth sciences. How did Earth's very first continental crusts actually form? We were talking about the Eochenal era, 3.8 to 3.7 billion years ago. The world was practically an infant. The rocks that survived from this era are called TTG rock standing for tonalite, trondhjemite, granodiorite.
And the origin of these ancient TTG rocks has fueled massive debates. The Earth today operates on plate tectonics, massive plates of crust sliding under one another, a process called subduction, which drags water down into the mantle and causes melting that forms our modern continents.
Right.
But 3.8 billion years ago, the mantle was much hotter. Many geologists argued that plate tectonics couldn't exist yet. They proposed a stagnant lid scenario where the crust was just one solid shell and the continents formed when massive oceanic plateaus simply sat there and melted from the bottom up due to heat plumes from the core.
Subduction versus stagnant oceanic plateaus. To solve this, our sources detail a massive study looking at 3.8 billion-year-old rocks from Greenland, specifically the Izua metabasalts and the Itzak tonalites. These are some of the oldest intact pieces of Earth's crust ever found. The researchers pulverized these ancient rocks, put them through a mass spectrometer, and analyzed their titanium isotope ratios.
And what they discovered was a highly specific, gradual increase of heavy titanium isotopes as the PTG rocks evolved, reaching an enrichment of up to plus 0.8 per mil.
Okay, I have to play devil's advocate here. I read the sources, I understand they found heavy isotopes, but why does a plus 0.8 reading prove plate tectonics? The early Earth was a wildly violent place. Couldn't these Greenland rocks have just formed from the catastrophic melting caused by a giant asteroid impact, or just the random chaotic melting of an oceanic plateau? Why does this specific ratio prove subduction?
It's the crucial question. To answer it, the researchers didn't just measure the Greenland rocks, they used high-powered computers to run complex thermodynamic models simulating every possible way to melt the early Earth's crust. They built digital simulations of melting a thick, titanium-rich oceanic plateau. They modeled catastrophic asteroid impact melts, and they modeled the slow, progressive melting of low titanium tholiated basalts, which is the exact chemical composition of crust being pushed down in a subduction zone.
So they essentially ran a simulation of 3 different early Earth baking recipes to see which digital recipe produced the exact isotopic cake they dug up in Greenland.
Exactly, and the thermodynamic modeling was definitive. Let's look at the oceanic plateau or asteroid theory. Those environments involve melting high titanium source rocks like EMRB or enriched mid-ocean ridge basalt.
Okay.
If you melt a rock that is already packed with titanium, the iron titanium oxides crystallize out very early and very differently. The simulation proved that melting a high titanium plateau traps the heavy isotopes in a way that leads to a flat or completely different isotopic signature.
It wouldn't produce that distinct climb to plus 0.8 per mil. The fingerprint would be dead wrong.
Right. The model proved mathematically that the only way to get the specific gradual increase of heavy isotopes found in the Greenland rocks is through a very specific sequence of events. The polybaric melting of low titanium tholiatic metasalts, followed by extensive fractional crystallization.
Okay, polybaric melting is a dense term. Break that down for us visually.
Polybaric means melting at continuously changing pressures. Imagine a slab of ocean crust being actively pushed down deeper and deeper into the Earth's mantle by tectonic forces. As it sinks, the pressure and heat continuously increase. It melts a little bit at 10 miles deep, a little more at 20 miles, evolving and changing as it descends.
Wow, okay.
That continuous changing pressure environment is the absolute hallmark of a subduction zone. An oceanic plateau just sitting on the surface melting from the bottom up does not experience polybaric melting.
So by ruling out the high titanium sources, because the isotope math doesn't fit, the only recipe left that physically works is the low titanium basalts melting at changing pressures. And that specific recipe definitively requires tectonic plates. It requires crust being actively pushed down into the mantle, melting, rising, and crystallizing.
The grand conclusion here is profound. The titanium isotopes essentially serve as mathematical proof that 3.8 billion years ago, the Earth was not a stagnant, inactive ball of rock waiting to cool down. The crust was forming in a proto-subduction zone. Early primitive tectonic plates were already crashing together, diving beneath one another, and recycling the crust. Titanium proves that the Earth was tectonically alive in its absolute infancy.
It just completely blows my mind. Think about the through line we just drew. We use this exact metal to paint the walls of our living rooms white. We use it to build lightweight frames for our bicycles. And that very same element is sitting inside a 3.8 billion-year-old rock in the freezing expanse of Greenland, holding the smoking gun forensic evidence that Earth's continents were born in the violent, grinding collisions of early tectonic plates.
It is the ultimate forensic tool. It seamlessly links the macro-scale movement of the entire Earth's crust 4 billion years ago to the micro-scale interactions of osteoblast cells in a rabbit's femur today, all governed by the exact same atomic properties.
Which brings us to the end of today's journey. Let's summarize what we've unpacked over the last hour or so. We started with a single element, titanium, an element so remarkably social, so stubbornly bonded to the Earth, that it defied the best chemists in the world for over a century before it could be isolated by Matthew Hunter.
A long time coming.
Yeah. And then we saw how the thermodynamic brutality requiring to unbake that bond, the extreme heat and cloying of the Kroll process, defines the tense, heavily guarded global supply chains of the 2025 industrial economy. I mean, we're talking about pitting U.S. domestic demand against geopolitical bottlenecks, tariffs, and energy crises.
We then explored its biological alter ego. We saw how manipulating its physical structure at the nanoscale, adding a touch of silicon to drop its elastic modulus down to 37 GPa to perfectly match human bone, allows it to seamlessly integrate into living tissue. By speaking the mechanical language of Wolff's law, we essentially ended the medical flaw of stress shielding.
And finally, we saw how the heavy and light isotopes locked within its crystal lattice serve as an indelible memory bank, surviving internal radiation and billions of years of weathering to hold the irrefutable evidence of the Earth's very first plate tectonics. It is an element that effortlessly straddles the line between the organic and the inorganic, readily accepted by our living cells, yet forged in the earliest, most violent days of our planet.
It is a profound reminder that the mundane materials we utilize every day have histories, capabilities, and complexities far beyond our typical understanding.
Which leaves us with a final thought to ponder as we close out. As we look to the future, as aerospace companies using this very titanium start talking seriously about building permanent colonies on Mars or the Moon, we know we cannot ship all our supplies from Earth. We have to live off the land. We have to utilize the alien crust.
It's the only way forward.
Right. It makes you wonder, what undiscovered Titan element is waiting in the red dirt of Mars right now? What seemingly mundane rock, currently sitting untouched on the lunar surface, is just waiting for us to figure out the chemical key to unlock it? What element is out there ready to become the foundational building block of our next century of survival if only we have the ingenuity to unbake it?
The universe is full of locked doors. We just have to be curious enough to find the keys.
And with that, we wrap up today's deep dive into the muddy, magnificent, and highly complex waters of titanium. Thank you for joining us on this journey, and keep questioning the world around you.